Okay. Good morning, everyone. Good morning. Okay, now we will start. Okay, today we will see BiCMOS technology. Okay, BiCMOS technology. Here, BiCMOS means bipolar junction transistor and CMOS technology. Okay, bipolar complementary metal oxide semiconductor technology. Okay, in this technology, okay, in the CMOS technology, we'll incorporate BJT technology to get the BiCMOS technology. Okay, why we are going for BiCMOS technology? Okay, because of this BJT advantages. Okay, here in the BJT technology we have, okay, speed is more compared to CMOS and MOS transistors. Okay, BJT offers higher some of the advantages here, especially speed. Okay, bipolar junction transistors offer higher speed compared to MOS. So that's why for some extra efforts, some extra complexity and cost, we can incorporate bipolar technology. Okay, to give higher performance. Okay, that's why we'll use BiCMOS technology. Here MOS transistors have limited load driving capabilities because of limited current sourcing and sinking abilities of P and N transistors. Bipolar transistors provide higher gain, better noise and high frequency characteristics than MOS transistors. Here if you see plain view of the BiCMOS, if you see here, just only indicating only NPN transistor. We are not indicating MOS, CMOS. The CMOS we have NMOS and PMOS. Okay, here that is not showing. Only indicating the BJT, bipolar transistor. Here. Okay, this one is emitter. This one is base, and here. Okay, we are forming this BJT in the N well. Okay, this all border is N well. In this forming the BJT. So this is collector and this is for contact. This is collector. Okay, here wafer is P type substrate. Here P type substrate. Here well is N well. Okay, this is plane wave. You see the internal structure. Okay, just indicating the here BJT is always formed on the surface of the buried N plus subconductor layer. Okay, this is buried layer. Okay, this layer is called buried layer. Okay, on that we will form the BJT transistor. Okay, this is oxide and this is base, emitter, collector. Okay, in between this one is the oxide to isolate between these two terminals. Okay, and this is P plus region. Okay, here we'll get NPN BJT transistor. Here collector is N, emitter is P, base is N. Like that, we will see the process steps in the next slide. Yeah. Here is taking the p-type substrate is taken. Okay, this is p-type substrate. Okay, here substrate is lightly doped. Then after substrate, the next step is okay depositing the oxide layer. Okay, silicon dioxide layer is deposited. This is silicon dioxide layer. Okay, in the every process steps, some of the procedures are same. Okay, after substrate, then silicon dioxide. Okay, which area we want, we will okay remove that area, and we can start. Then we can start there. Okay, initially we should not start from the wafer itself. Okay, why we are not starting in the wafer itself before this oxide layer? Okay, because when we start on the surface of substrate or wafer, that wafer may break, or some uh, the properties may change. It may break, or that properties may change. So for that purpose, first depositing insulating layer, that is silicon dioxide layer. Then which area we want, we will remove that portion. There we will start the process. Now, okay, this is BiCMOS. So here we are taking BiCMOS. So in the BiCMOS we have bipolar transistor and NMOS and PMOS. Okay, for that purpose, okay, first we need bipolar transistor. Okay, we need to form the BJT. So we are making the one window or opening for this BJT. Means you use okay this appropriate mask to remove this area. Using UV ray we can remove this area. Then here after one window is opened through oxide layer, then we need to form the N plus buried layer. Okay, this N plus buried layer is used uh, to reduce the resistance of this uh, collector. Okay, externally in the NPN transistor, this collector resistance should be low. Okay, for that we will use N plus buried layer. Okay, N type impurity is heavily doped. This N type heavily doped buried layer is formed. Okay, in this window. Okay, then you will see next step. Then you will deposit epitaxy layer over this surface of the piece substrate. We will deposit p-type epitaxy layer. Okay, in the CMOS also we used epitaxy layer. Okay, here also we will use epitaxy layer. Means here we need to form the PMOS, NMOS and BJT transistor. Okay, here p-type epitaxy layer is grown on the entire surface. This one. This is epitaxy layer. Then after that we need to form the wells. Then again we are depositing oxide. See, for every step, okay, we cannot start on this one. Okay, we will deposit oxide over this surface, and we need to form the wells. The entire surface is covered with oxide layer, and two windows are opened through the oxide layer. Okay, these windows are opened by applying some suitable mask. Okay, some applying some suitable mask. Okay, initially this oxide layer is applied uniformly on the surface of this epitaxy layer. Okay, we will use suitable mask and apply UV rays entire surface. Okay, wherever this UV rays are allowed, okay, this material will be softened and remaining area will be hardened. Okay, this is softened by using etching forces, by using some solution, that is hydrofluoric acid. Okay, some acids. Okay, we can remove this area. Okay, that is etching. That process is called etching. Etching process. Okay, that is given here directly. Okay, these windows are formed for the wells. Now in the next step we will see well. Okay, now here N well means this is PMOS. Okay, here this is for BJT. BJT transistor. Here we will form NMOS. Now here N plus Barry layer. Okay, forming the N well. Okay, means N well means diffusing N type material. Okay, N type semiconductor. Okay, to form the well here. To form the L. Here also N well. By using diffusion process, okay, these wells are created. Then here this N well acts as a collector of the BJT. Here if you see collector, this N well acts as a collector, and this collector area should be more. This collector area should be more. Okay, in the BJT, this collector area should be more. To for the output, your output impedance should be low. Output impedance should be low, and the power dissipation should be minimum at the output. So the this area will be more, means this whole area will be collector terminal. The next step, okay, we will form the P well. Okay, this is epitaxy layer. So we need no need to form the P well here, but directly we can take here. Okay, we can take diffusions, source and drain. Okay, this is epitaxial layer. Oh, here forming well and well, so no need of taking P well here. P well here. So now the entire surface is covered with Thinox and polysilicon and are patterned to form the gate terminals of the NMOS and PMOS. Now the previous only this oxide is there here. Okay, this oxide here, oxide is there. Oxide is there. The next step if you see, so we will apply polysilicon for the gate. Now here we need one. Okay, here one transistor. You need one transistor. Here MOS. Here one MOS transistor. Here BJT. So by using here also same suitable mask. Okay, we will remove the some of these particular areas. Yes, small windows. Remove these areas here also. Removing these areas, and uh, applying the polysilicon material for the gate terminals. Okay, applying polysilicon material for the gate terminals. Here this polysilicon also by applying photoresist. Okay, by applying photoresist, by applying photoresist and polysilicon, okay, by using a suitable mask wherever this polysilicon should be present, okay, wherever this polysilicon should be present, that will remaining this okay, oxide will be okay, remaining this polysilicon will be removed, this areas, okay, this areas removed. See here, only this area polysilicon is present, remaining areas removed. Okay, that is for the gate terminals. Now next for source and drain we'll use diffusion. In the next slide use diffusion. Through the third window, the P impurities are moderately doped to form the base terminal of BJT. N-well acts like the collector terminal. Here N-well acts as collector. Now here P-type material is okay, P-type dopants are okay doped using in the N-well. Here for base terminal, okay, here, okay, this is base. Okay, using p-type semiconductor, this p-type impurities are doped into this n-well to get the p terminal. Means this is base. Okay, this p-type acts as a base. Next okay, next diffusions. Okay, here n-type impurities are heavily doped to form. Okay, here at a time we are doping the n-type impurities. Here if you see, okay, n-type diffusion, this is n-type and this is n-type. This is for emitter. Okay, this is for emitter and this emitter, this is okay n-type. So here also n-type. At a time you are depositing by using diffusion process. Okay, remaining area will be you will use some suitable mask to avoid that area and only this our required area will be diffused. Okay, here in the collector and well, okay, here we will use okay some heavily doped small area will be diffused to take the connection for the collector, this one. Okay, okay, small area we can dope, okay, heavily doped, that is for the collector terminal. Now here n diffusion is over, here p diffusion for PMOS. Here for we will use PMOS. Okay, p diffusion. Here source and drain region of NMOS. Here source and in region of NMOS. Second emitter terminal of BJT. Okay, here BJT, this is emitter terminal. Next N-well collector region for contact purpose. Here N-well collector okay region you will use small amount of doping. Yeah, now P diffusion. Here P-type impurities are heavily doped to form at source and drain region of PMOS. Okay, this is PMOS transistor in the N well. Okay, to form source and drain region of PMOS. Next, here P base. Okay, here the BJT. Okay, base terminal, that is P type material. So you will use here also same P type. Okay, doping, diffusion for the connection. Okay, contact purpose. Here also small area can be doped here into P base region for contact purpose. Now we have source, drain, gate. Here also source, drain, gate. Now this is collector. Okay, this is base. This is emitter. Okay. Next, see, you will deposit metal and you will take contact cuts. The entire surface is covered with thick oxide layer, that is silicon dioxide layer, SiO2 layer. Okay, entire surface depositing with silicon dioxide. Then we will use some suitable mask. Okay, wherever our contact cut or contact hole is required. Okay, you will use one mask to remove that area and we will keep oxide as it is. Means we need here hole, contact hole. Here also we need hole. Here also we need hole. Here also, here also, here also. Here collector. This is base. This is emitter. Okay, this area will be removed and the remaining area, this oxide is as it is. See, okay, we can deposit metal, aluminum, like that, external terminal. Okay, this is oxide. So this oxide is used to isolate between these beside terminals, drain or source and gate. Here in the BJT, emitter base collector, these are isolated by using this thick oxide layer. Here entire surface is covered with thick oxide layer and is patterned for contact cuts. Okay, here contact cuts are formed. Okay, next step we will deposit here metal. Yeah, metal contacts are formed. Okay, here also same procedure. Total this okay. Initially, here step is directly given. This total area will be deposited. This total area will be deposited. Okay, then you will use some suitable mask wherever uh, this metal will be removed. Means this area will be removed. Okay, this empty places, this area will be removed. Only these contact holes are there. There this metal should be present. Remaining area metal should be removed. Okay, then we will use suitable mask. Okay, and we can lift off this unwanted metal. Okay, lift off this unwanted metal. Okay, this removing of unwanted metal is called lift off process. Okay, removing of unwanted metal is called lift off process. Now after removing this unwanted metal, here we can see only these terminals, this brown color. If you see here brown color, terminals will be present. Remaining area is remaining terminals is isolated by oxide layer, blue color. Okay, now this here we can see this is NMOS, PMOS, okay, BJT, NPN, BJT. Okay, collector, base, emitter. Here source, gate, drain, source, gate, drain. Okay, here dimensions of source and drain are equal, so we can take here source as drain or drain as source also, because these dimensions are okay same, ideal. So we can take as in place of source we can take drain, or in place of drain we can take source, okay, like that. Okay, this is by CMOS process. Okay, in the same way for fabricating the, okay, implementing bipolar technology and CMOS technology, okay, to get the higher performance and high efficiency. But using this bipolar technology, okay, this fabrication process is somewhat complex, but performance is more. Okay, now the present technology is BiCMOS technology is using. Okay, now time is getting out. Okay, next class we will see electrical properties of, okay, mass circuits. Okay, now advantages of BiCMOS over CMOS technology. Using BiCMOS process, design of analog amplifier is possible, except input circuit. The remaining stages and output drivers are realized using bipolar transistors. Here, this technology is used for input, output, and driver circuits, while CMOS technology is used for logic only. And this technology is low delay, sensitive to load, high output drive currents. Okay, these are the advantages of BiCMOS or CMOS. Okay, in the next class we'll continue electrical properties of mass circuits. Okay, now any doubts regarding this lecture? Okay, now I will send this PPT also. Okay, we'll join in the next class. Okay. serial numbers.